All right, quick review from yesterday. We started off talking about the kind of history of chemistry, okay, that it was something that was mostly a tool and then became kind of a secretive thing that people did during the Middle Ages, the alchemists, and then became more of a scientific branch of science, okay, using the scientific method. Okay, we learned about a few important people, okay, John Dalton being probably one of the most important, as he is the one who developed the atomic theory, which has how many points? 4. Okay, so all matter is made of tiny indivisible particles called atoms. The atoms of any one element are identical. Atoms of different elements are different. Okay, atoms can combine in simple whole number ratios to form compounds, and in a chemical reaction, atoms can be separated, joined, or rearranged, but they cannot be turned into atoms of another element. Okay, those are the 4 points. You definitely need to know those. And then we went into the models. Okay, Dalton's the person who came up with this, so he was the first person to come up with a model. He said, atom is a sphere. Okay, which was quickly disproven when electrons were discovered. Okay, and we went to plum pudding after that. And then there was disarray for a while people were arguing whether there was plum pudding or separate particles or a nucleus or whatever. Okay, until Rutherford came along, and what was his experiment called? The gold foil experiment. Okay, where he shot the X-rays at the piece of gold foil, and a whole bunch of them got through, okay, but some were deflected, proving that the atom is not a big solid sphere, but made of a tiny dense nucleus, okay, surrounded by electrons, right? And then there was argument about what are the electrons doing, and then de Broglie came along and discovered that electrons can actually change their energy and move further away or closer to the nucleus, okay, giving us our currently accepted model of the atom, the electron cloud model. Okay, at the end of the day yesterday, we had just finished going over how I would ask about the structure of the atom. Okay, so it was a quick review. On an exam or a quiz, like this Friday, okay, I would ask you to draw a picture of a particular element's atom. Okay, so if I was asking you to draw an atom of, let's say fluorine, okay? You draw an atom of fluorine, okay? Then what we would do is figure out how many protons there are. Okay? How many proteins in a fluorine atom? 9, because its atomic number is 9. 9 always tells us the number of protons and the number of electrons, because they have to be equal, right? They're oppositely charged, and an atom has no overall charge. Okay, so we know that the electrons, okay, smaller marker. Electrons, okay, are going to be 9. Smaller marker. Okay, and the protons, okay, we'll call those. We'll just represent those with a positive circle. Okay, those are also going to be 9. And how many neutrons are there? 10. Okay, the atomic mass is 19. Okay, and to calculate the number of neutrons, we go atomic mass minus atomic number. 19 minus 9 is 10. All right, so we would say neutrons equals 10. So then we would do this. I should have picked a smaller atom. Okay, that wasn't very smart, but okay, that's the way we went. Okay, and then we would have around that, okay, 9 electrons. And call it the cloud, and we'd be good. Okay, everybody all right with that? Okay, so make sure you got the protons and the neutrons in the nucleus with the right numbers. Okay, put the electrons in a cloud around the outside. Do a better job of drawing it than I do. I have 0 artistic ability, and so that's why my pictures always look like crap. Okay? All right, questions on that? That's what we left off with yesterday. Everybody's good there? All right, so as we currently understand it, an atom kind of looks like this. Okay, there's the central dense nucleus where the protons and the neutrons are, okay, and the electrons orbited on the outside. Okay, their orbitals are not all the same radius, okay, like it shows in this picture, okay, but they are going to have a high probability of being found in certain places within the cloud, okay, based on the energy of those electrons. Okay, if they're in a higher energy state, then they're going to be further away. If they're in a lower energy state, they're going to be closer to it. Right? But they can move all over the place. So we can't actually ever say an electron is there. Right? We can say there's a high degree of probability of finding an electron in like this area. Okay? We could say that, but we can never determine or state that it's right there at any one time. Okay? All right, so the big deal here, and this is partly Rutherford's doing, okay, is to illustrate that an atom, excuse me, is actually a lot of empty space. Right? The nucleus is central and very dense, so very small. The electron cloud actually makes up the vast kind of volume of the atom. Okay? But electrons are tiny. Okay? Way, way smaller, like orders of magnitude smaller than protons and neutrons. So they're buzzing all over the place inside this region where they can likely be found. Okay? It does mean that the atom is a lot of empty space. Okay, kind of like if, and this is kind of why Bohr's model persists, the planetary model. It's kind of like our solar system. Okay, our solar system is huge, but when it comes right down to it, it's a lot of empty space. You know, there's the 8 planets and the Kuiper belt objects and the asteroid belt. But I mean, really, if you sent a spacecraft out, the likelihood of it hitting anything on its way out of the solar system is pretty slim. Okay, because there's just so much empty space. That make sense? Okay, so if all atoms are made of protons, neutrons, and electrons, so all matter is made of the same things, how is it that we have all these different elements that all have different properties? If they're all made of protons, neutrons, they're all made of the same stuff. Why are they different? They have different numbers of those same 3 building blocks. All right? And the most important particle of the 3, okay, is the protons. Okay? All elements have different numbers of protons in their nucleus, and it is the number of protons that determines both the physical and chemical properties of each element. Okay, so make sure you have that stuff that's underlined there, okay, highlighted or underlined or written out in your notes. Okay, that is why we have so many different elements. Every element has a different number of protons. Okay, so on this topic, Dalton's 4th point of his atomic theory says that in a chemical reaction, you cannot change the atoms of one element into atoms of another element, okay? If you start out with sodium and chlorine and lead and oxygen, you're only going to have those 4 elements on the product side. You're not going to change them into anything else. Is there a way to change the atoms of one element into atoms of another element? There is. You have to change the nucleus. If you change the nucleus, in particular, you change the number of protons in the nucleus, then you change the element. Okay? When Dalton came up with his theory, okay, the technology available to do that and the understanding of how it worked wasn't there. But he did make, in his point, he said, in a chemical reaction, this cannot happen. But there's a physical way to do it. And that's modifying the nucleus. What are the two ways we generate nuclear power? They both start with F.
Force.
Close, close. One means to split, one means to force together. Fission and fusion. Okay, those are the two ways that we can generate nuclear power, fission and fusion, right? They both involve changing the nucleus of an atom, right? Now, one of them happens in nature all the time. In fact, we depend on it. Nuclear fusion is what powers the sun. Okay? So what goes on in the sun is made mostly of hydrogen gas. Okay? But the sun is enormous. Okay? It accounts for 99% of all the mass in our solar system. It's almost all in the sun. Okay? So it's so massive that its own gravity crushes the hydrogen atoms together. Okay? And when you crush the hydrogen atoms together, they fuse. They go from being separate hydrogen atoms to being a single atom of helium. Because they go from having one proton to two. Okay? The sun fundamentally changes what it's made out of, okay? By simply crushing what it's made out of together to fuse it into a larger atom. Really, really big stars can do that with even larger atoms. Okay, so if you had like a red supergiant star, okay, it might actually be fusing things like carbon together, okay, and making even bigger atoms like iron and things like that. You have to have a lot of mass for that to work, but really, really big stars can do that. All they're doing is forcing those atoms together under such incredible pressure and force, okay, that they literally change what they are. Okay? They fuse together to become a bigger atom. So it's possible, and it does happen in nature. Okay? But it's not something that happens like on your kitchen table. Okay? Everybody kind of follow me there? That's actually something we're looking to be able to do. How many people have heard of cold fusion? Okay? It's supposed to be like this revolutionary form of energy for later down the road. Okay? Being able to do this fusion reaction anywhere. To power a car. Okay? Things like that. Right? It's kind of difficult to do, obviously, because we haven't achieved it yet. Okay? The other way to change the nucleus of an atom is by splitting it. Okay? That's nuclear fission. That's the form that we use to generate electricity. Okay? So what we do in nuclear fission is we take really big, unstable atoms like uranium. Okay? So if we got like a really, really big, okay? Really, really big. I'm not going to draw all the particles in a uranium atom because I'd have to draw 238 particles. Okay, or 238, yeah, 238 particles. Okay, I'm not going to do that. So I have a really, really big atom. Okay, and then we just fire like neutrons at it, free neutrons. Okay, a little particle emitter. Okay, when those neutrons hit it, it's like the beginning of a game of pool. Okay, you got a break, right? You got the triangle made up of the balls. Okay, so the cue ball comes in, it hits that, and they split apart. Okay, it's kind of like that, except it doesn't split into that many pieces. Right? But it splits, it'll break apart. And when it does that, it releases a whole bunch of energy. Okay? Even on a small single atom scale, it's a lot of energy. Okay? Well, once you start one breaking, it can break ones that are nearby, and they can break others, and eventually you get a chain reaction, and you get a lot of heat. Okay? You get a nuclear reaction going on. Okay? When that's done, you have different materials than you started with. Okay? Uranium can be broken down into radioactive forms of lead by losing 10 protons and a bunch of neutrons. Okay, making some sense? So it's not a chemical thing. We can't change an atom of one thing into an atom of something else by a chemical means, but we can do it if we have the right technology by a physical means. Okay, everybody all right with that idea? Okay, so that's the two ways you can actually alter the nucleus of an atom. Okay. Eventually How many people have the workbook already printed? Okay, if you do, there's questions on that on like the second page. Okay, for the rest of you that don't have it, I'm going to put them up here, but they're going to be a little hard to read because they'll be small. Okay, so there are 12 questions. Okay, I would like you guys to work on those for the next little while. Okay, good complete sentence answers. Okay, all of this stuff is stuff that we've talked about either yesterday or today. Okay, put it in your own words. Okay, some of these are talking about the models, so you can describe those models in your own words or draw pictures or whatever works best for you. Okay, I'll give you, let's say, half hour, 40 minutes, okay, to work on those, and then we'll go through them together. If you have questions, let me know. Okay, put up your hand or come up and see me. Okay, guys, let's quickly go through these. If you need to add anything or change anything, just do that kind of on the fly here. The idea of the atom was first proposed by whom?
Democritus, and it was rejected because he couldn't prove it because it was real.
Okay, yes, Democritus is the right answer. Yes, he couldn't prove it, and also because was there already something people liked better?
The elements.
Right, the 4 elements idea, right? That was more tangible to the people. It wasn't right, obviously, okay, but it was more tangible and more real and made more sense than imaginary little particles that no one can see. Okay, that sounds crazy. Okay, I mean, you can imagine someone from that time, that would sound even crazier. All right. Number 2, the elements the Greeks believed all matter was made of?
Fire, water, air, and earth.
Right, fire, water, air, and earth. Okay, those are the 4 elements. Okay, why was that a logical conclusion again? It was something tangible. It was something that made sense to them. They could explain the behavior and makeup of things that they encountered in their daily life.
Because if you were to take steam as an example, you would need fire, water.
Yeah, exactly. Fire, water, and you'd make air also, right? Because steam would be a gas. Okay, so again, it was just something that they could understand. It made more sense to them. Number 3, in the Middle Ages, some people inadvertently did a lot of work to develop the science of chemistry. They were the alchemists. Okay, what were they trying to do?
Change one element to another.
Right, okay, get rich by turning cheap stuff like lead into expensive stuff like gold. Okay, they also had a goal of creating the elixir of life. That didn't work out well for test subjects generally. Okay, usually it was like mercury and arsenic and things like that that are highly toxic, and so yeah, the elixir of life usually was the elixir of quick death. Okay. All right, in the 1700s, a man used the data from many experiments to develop an idea on the structure of matter. Okay, who was it?
Dalton.
It was Dalton. Okay, his theory had 4 points. Okay, just to be quick here, the 4 points need to go something like this. In your own words is fine. Okay, point number 1, all matter made of atoms. Okay, if you have something along those lines, that's good enough. All matter made of atoms. Okay, second point, atoms of the same element are the same. Atoms of different elements are different. Okay, something along those lines is a good summary of the second point. Okay, the third point you can't really summarize. All the parts of it are important. Atoms can combine in simple whole number ratios, that's important, no half atoms, okay, to form compounds. Okay, so compounds are formed by atoms combining in whole numbers. And the fourth point tells us what happens in a chemical reaction and what doesn't happen in a chemical reaction. Okay, what does happen is that atoms can be separated, joined, or rearranged. Okay, any one of those things will work. Okay, and here's kind of what that looks like, but they can't be turned into atoms of different elements. Okay, so if we're looking at what a separation would look like, okay, a separation would look like this. I have water, and it is separated, okay, into its elements, a la Mark Watney. Okay, that's how he nearly blew himself up in The Hab in The Martian, if you've seen that movie or read the book. Okay, a joining reaction would be the opposite. So I'd have like Na plus chlorine would make NaCl. This would be a 2 and a 2 here. This would be a 2 and a 2. Okay, so that would be separation. That would be joining. And then a rearrangement would look something like this. So we might have okay. It's all the same things. I don't make any new elements. I've just rearranged them. They go together with somebody else. Okay, those would be examples of separation, joining, and rearranging. Okay, we'll be looking at reaction types like that later on in the unit. All right. Now, looking at this theory, so question number 5, what things do you know of that can prove some of his ideas wrong? Okay, what's something we can do now that he said was impossible? He said atoms are indivisible. Are they? We can split them, okay? Oppenheimer figured it out, right? We can split the atom, so they're not entirely indivisible. They're indivisible by a chemical means, okay, but not by a physical means. And we also talked yesterday about something called an isotope. Carbon-14 was the example I used, okay, where it has the same number of protons, but it has a different number of neutrons. So in that way, a small percentage of any element's atoms are slightly different. Okay? They're not all 100% identical, but they're close enough for that to still be considered true. Okay? All right. Describe in your own words the models of the atom discussed here. Okay? Give a brief explanation as to why each was rejected or changed over the years. Okay? Do you think our current model may change and why? All right, so just quick summary. Solid sphere. Okay, that was the first one. Rejected because we discovered. What discovery led to the rejection of the solid sphere?
There was like an X-ray and you couldn't see the atoms, so it would be big enough to be like a sphere.
Okay, partially, but we actually discovered a particle that led us to reject it.
Electrons?
Right, when we discovered electrons, it was found that, well, the solid sphere doesn't explain differently charged particles. So we came up with, the next one was? Starts with P.
Plum pudding.
Plum pudding. Okay, plum pudding is still a solid sphere, okay, but it's got the electrons embedded on the outside. Okay, and then plum pudding was rejected when protons were discovered. Okay, then there were a whole bunch of models in between there that didn't work. And then Rutherford did his gold foil experiment and came up with the nuclear model. Okay, and then we went to eventually the de Broglie model because we discovered that electrons behave differently than was originally thought. Okay, something along those lines. As long as, let's say, on a multiple choice item, you'd be able to go, that's a plum pudding, that's a Rutherford model, or that's an electron cloud, or that's a solid sphere. Okay, as long as you can recognize it. All right. Okay, as our knowledge increased, we discovered the atom had smaller parts. Okay, what are the 3 parts of the atom?
Proton, neutron, electron.
Okay, where do I find the protons and neutrons?
Near the nucleus.
In the nucleus, yes, definitely. Okay, and where do I find the electrons?
On the outside of the nucleus.
Right, in the
Sphere? No.
cloud, in the cloud, yeah. Okay, in the cloud. If you wrote surrounding the nucleus, that would also be fine. Okay, as long as you specifically state that they are not in the nucleus. Okay, electrons surround the nucleus in the cloud. Okay, that would be good. Okay, protons are obviously positive, neutrons are neutral, electrons are negative. Okay. For number 8, I say 1 cubic centimeter here, but what I really should say is like 1 million atoms, okay, of lead are much heavier than 1 million atoms of carbon, to be a more fair comparison. Okay, why? The same number of atoms.
Because lead is a metal and carbon is a gas, right?
Actually, well, carbon can be a gas if it's hot enough, but at room temperature, it's actually a solid. That's what charcoal, graphite, and diamond are all made out of, so it's solid. Why else?
Because their atomic mass is different.
Why is their atomic mass different? You're definitely on the right track. Yes, it is because their atomic masses are different. What makes their atomic masses different?
But the levels of one dense.
Okay, it could have to do with density. Density is kind of caused by what I'm looking for.
The difference of number of protons?
Right, the atoms are bigger, okay? A lead atom, okay? A lead atom has 82 protons. A carbon atom has 6, okay? So if I have the same number of atoms of each one, this is gonna be way, way heavier, okay? They're just a bigger atom, and if I have the same number, okay, then obviously that one's gonna be much, much heavier. All right, question number 9, big or small? Big, yeah. I mean, think about this. You have a bow and arrow and you're trying to hit a target, okay, that's, 50 meters away. The bullseye is harder to hit than just hitting the general vicinity of the target, okay? We want a big target, okay? A bigger atom is going to be easier to hit. A bigger atom is also going to be easier to break. And it will release more energy because there's more to it. Okay? You would definitely want to use a giant atom like uranium, okay, that has 238 particles in the nucleus versus an atom of lithium that has 7. Okay? You're going to have a much harder time hitting a lithium atom than a uranium atom. Okay, and atoms are indivisible. Why was this statement believed for so long? Okay, why is it still somewhat true provided no human technology is present? Okay, well, it was believed for so long because nobody could do it. Everybody says that's impossible until somebody proves otherwise. Okay, so we split the atom. Now we know atoms are divisible by a physical means. Okay, and it is still somewhat true because atoms don't generally split on their own. Certain atoms break down, okay, those would be our radioactive elements. They do break down and release neutrons, but generally speaking, they don't just split and release a whole bunch of energy. Okay, they might be radioactive, they might release some radiation, some energy, okay, but most things do not. Okay, number 11, from what you know of the structure of the atom, how do you think it stays intact? Why do the electrons not fly off or protons separate from the nucleus?
Because the protons and the electrons would repel from each other.
Repel or attract?
Repel.
The protons and electrons will?
Attract.
Right. Yeah, you're right. Yeah. So the protons and electrons will attract because they're opposites. Opposites attract. Okay. Now, what about the neutrons and the protons? They're smushed together. Yeah, the neutrons have no charge. If you put the most positive, purely positive thing there is in existence next to something that's neutral, that neutral thing looks negative next to it. Okay? There's this thing called the strong intermolecular force that kind of holds them together, but it's basically an attractive force, okay? An electromagnetic force between the two. Okay, and then number 12, okay, we were talking about this the other day, okay, when chlorophyll gets excited, gets hit by sunlight, okay, the electrons get excited, they pop up to a higher energy level, and then as they fall back down, they release the energy that they have absorbed, and that energy is what is used to break apart carbon dioxide and water and reassemble them into glucose and oxygen. Right? So this energy source for photosynthesis is electrons jumping or making a quantum leap from one level to another and then releasing that energy as they fall back down, same way as a glow-in-the-dark material does. All right, any questions on that stuff? Okay, that stuff is definitely game for this Friday's quiz. Okay, I'm going to give you about a 2-minute break here, and I'm going to put on the board which practice quizzes will be good for you to have a look at, okay, for this Friday's quiz. Okay. Oh, you need one more. Okay, so guys, you now have your, listen up guys. What you have in front of you is not just the periodic table. It is also your data sheet for this course. So keep this, protect it, okay? Don't lose it. I mean, I do have extras over there, but once those extras are gone, I'm not printing any more. There's probably enough for 3 classes, but okay, let's not be willy-nilly with our resources. So obviously now you're going to have that, and you're going to be using it here for some naming stuff. Okay. So for naming compounds, this is probably, at least at first, going to seem familiar. You learned how to name simple binary, ionic, and molecular compounds in Science 9. Okay? We'll be reviewing that today, and then doing a little bit more with it and showing you a few new things, okay, tomorrow. All right? So, an ionic compound. What makes up an ionic compound? There's one metal, a metal and a non-metal. One thing from each side of the staircase is what makes up an ionic compound. Okay, so we get one metal, that's the things on the left, one non-metal, things on the right of the staircase. Okay, if we get two of those things going together, okay, then that makes an ionic compound. Now, ionic compounds work differently in terms of their structure and their bonds than do molecular compounds. Okay? Ionic compounds are very much about, this is going to sound terrible, getting what they want. Okay? In an ionic compound, the desire of both the metal and the non-metal is to have a certain electron configuration. Okay? So this is where, the other day I was saying that we still sometimes look at Bohr's model of the atom. Okay? When we talk about ionic compounds, we actually look at Bohr's model. So if I have a sodium atom, let's say, okay, so is sodium a metal or a non-metal? It's a metal, it's on the left. Okay? A sodium atom has 11 protons and it has 11 electrons. When we're looking at where electrons are generally found, okay, we call those places orbitals. Okay? In the first set of orbitals, there is only enough room for 2 electrons. Okay? In the next set of orbitals, there's room for 8. Okay, and they generally do this because of repulsion. Okay, now that's only 10 electrons. Sodium has 11. So that means it's got one more ring. This ring can hold 8, but it only has 1 in it. All elements want their outer layer of electrons to be full. Okay, for whatever reason, that's what they want. Okay, all atoms want to have their outer shell or orbits of electrons to be full. So, sodium's got 2 options for how to do that. It can find a home for 1 electron, so find somebody willing to take it off its hands, or it can find 7 more to fill that shell up, which is easier. Would it be easier to find a home for 1 electron or find 7 more electrons that you have to take from someone? Yeah, find a home. Yeah, get rid of the 1. Okay? Metals are always looking to give away electrons because their shells are always less than half full. Okay? Non-metals, on the other hand, are always looking to pick some up because their shells are more than half full. Okay? So non-metals want to pick up electrons, okay? And metals want to give them away. So what happens with an ionic compound is the metal will give its electrons to the non-metal. So something that goes well with sodium would be chlorine. Okay? Chlorine has 17 electrons. Okay? Okay? So in the first shell, just like sodium, there are 2. Okay? In the next shell, there are 10. Or sorry, 8. That's 10 in total. Okay? And then another 7. It's 1 short of having that full outer shell. Okay? Does it seem like these 2 should get along? Yeah, they each have what the other needs. Sodium needs to get rid of an electron, chlorine needs to pick one up. Right? So they'll form an ionic bond. Okay? An ionic bond simply means an electron is donated and received. Okay? Donated by the metal, received by the non-metal. Now, they both have a full outer shell. Are they both happy? They are. Do they need each other anymore? They do not. Okay, don't read into this sociologically, okay, because we're not trying to make statements about relationships or anything here, okay? But in an ionic compound, the bond isn't very strong because they're no longer dependent on each other for what they needed, okay? They got what they needed, or wanted, or whatever, okay? They got that outer shell to be full, okay? So ionic bonds are easily broken. Right? It's why ionic compounds typically dissolve easily in water. Okay? The two charged parts just split. Okay? Molecular compounds are the opposite. They don't donate their electrons. They don't trade them. They share them, which means that they're so utterly dependent on each other they can't fathom an existence without the other. Okay? They have to be together to have their outer shells full because they're sharing the electrons instead of giving them up. Okay? Everybody follow me on that? So that's how those two compound types are different. So an ionic compound is always going to be a metal and a non-metal because they're willing to give away and take the electrons, but a molecular compound is two non-metals together sharing their electrons, okay? Which is a much stronger bond, okay? Because they can't split or they won't be happy anymore. All right, so as we were saying here, ionic compounds occur when a metal from the left side and a non-metal from the right side react to form a new molecule. Okay, in these molecules, electrons are typically lost by the metal, gained by the non-metal. Okay, thus both have their outer electron shells full. Okay, and that's exactly what they are looking for. Okay. So let's see what we remember from last year. Is that an ionic compound? It is. Lithium is a metal. Fluorine is a non-metal. What would I call it?
Lithium fluoride?
Lithium fluoride. That's it. Okay? When you're naming ionic compounds, you write the name of the metal, exactly as it appears on the periodic table, and you write the name of the non-metal, and you change its ending to "ide." That's it. Okay? That rule applies to any compound that is made of a metal and a non-metal. All right? What if I had this stuff?
Is it barium chloride?
Barium chloride. Okay? In an ionic compound, we never use a prefix, because there are probably a lot of people whose gut reaction was like barium dichloride, okay? Because we feel like we have to mention that there are two, okay? In an ionic compound, you do not put prefixes in. This is the only way that barium and chlorine can go together. Barium has 2 electrons it needs to give up. Chlorine can only take 1 each. That's why there are 2 chlorines there. Okay? It needs 2 chlorines to make homes for the 2 electrons that it needs to give up. Okay? That is the only way that those 2 things can go together. How many people remember this? Drop and swap, or swap and drop. Okay? The reason you do that when you're making up the formula is to make sure that the number of electrons is balanced. Okay? To make sure that you've accounted for the fact that barium has 2 electrons to give away, and chlorine can only take 1 at a time. Okay? That's why I would need 2 chlorines to make that work. All right, is that ringing a bell from last year a little bit? Okay, so we'll go over kind of the simple ionic compounds tomorrow, okay, and then we'll go into some stuff that you haven't done before, okay, it's a little more complex, and then we'll move on to molecular compounds. We'll probably get through all of the teaching stuff for naming tomorrow, and we'll spend Friday practicing. Okay? All right, good job today, guys.